So we're going to start this off with the history section because we really want to see where it came from and how it has gone from there. And it all starts off in the early 1900s of 1925, where Julius Edgar Linenfeld discovered the concept of field effect, which he tried to use that to make the first transistor, but he was never really able to make it work. Then 1948 came around. At Bell Telephone Laboratories, three physicists named William Shockley, John Bardeen, and Walter Brattain, they made the first transistor. It was the bipolar junction transistor, and because of how much technology that this first successful transistor paved its way for, they were all awarded Nobel Peace Prizes, and it is basically considered the most important thing ever invented for the 20th century. Then 1959 came around, where Muhammad Atala and the Kang made the metal oxide semiconductor field effect transistor called the MOS or the MOSFET. It is the most widely used transistor in all modern electronics. It is considered basically the most manufactured device in all of human history. Then lastly, in 1965, a person by the name of Gordon Moore predicted a trend that is called Moore's Law, where the numbers of transistors per square inch would be doubled for every single year. And it held up for a pretty long amount of time because it's still going now. But it doesn't technically apply anymore, but it's not doubling, but it is still increasing exponentially. And then by 2036, it is predicted that it will actually become obsolete because it will just become harder to fit more. It's still pretty crazy if you just take it into perspective of just how many that is. Because if you just search it up, one third generation Intel Core processor has approximately around 1.5 billion transistors, which is, in comparison, a fifth of our world's current population, which is possible because transistors around now are about 10 to 20 nanometers.
Thank you, Vyn, for a little bit of history. Now let's talk about what transistors are. Transistors are going to be a semiconductor device, and some can amplify signals and others will act as electrically controlled switches. Either way, transistors are an essential component to every electronic circuit. So we can see here that there are many types of transistors, and let's start with BJTs, which are bipolar junction transistors. Bipolar meaning they use both electrons and holes to require conducting a current, and junction means that they have both a P and an N junction. They operate both majority and minority charge carriers, but BJTs have three terminals, including emitter, base, and collector. When we look at NPN versus PNP, they're going to be very similar and quite the opposite of each other. So the first thing with them, NPNs are going to have a 2 N-type semiconductor material, and they're going to be separated by a thin layer of P-type semiconductor. And the second thing is NPNs have the majority charge carriers in electrons, while holes are going to be the minority charge carriers. And when you think about PNPs, they're going to be flip-flopped. Looking back at the transistor type tree, we can see that we have field effect transistors to talk about as well. So FETs, they are 3 terminals as well, and they consist of gate, drain, and source. JFETs have an N channel and a P channel. So the junction field effect transistors are basically the earliest and the simplest type of JFETs. And JFETs are commonly used for switches, amplifiers, and resistors. While JFET comes in both N channel and P channel, the N channel is going to be preferable than the P channel JFETs. When it comes to speaking about MOSFETs, MOSFETs are going to be the enhancement and depletion. MOSFETs are metal oxide semiconductors field effect transistor. They're basically going to be the most common, and Vyn mentioned that a little bit about them. They are going to be advantaged over everything that we've basically talked about so far. MOSFETs have four terminals, drain, source, gate, and the body. And they are served as an advantage just because they mainly offer at a high input impedance and a low output impedance. And they're great for switches and power circuits. They also come in N channels and P channels. All in all transistors are classified depending on their structure, and each type of transistors have their own characteristics and advantages, and so that's why they have so many different types. And transistors are also based on their application. And it leads us right into transistor functionality. Over here on the right, we can list from top to bottom, which is also from the simplest to the most complicated functions. With these two, we can start with small signal transistors. They're going to conduct small signals, but sometimes these transistors are also used for switching purposes. Next to it, small switching transistors are primarily used for switching, but they can also be used for amplification. Both of these are available in the form of NPN and PNP transistors. A step up from these two are going to be starting with power transistors. They conduct high power amplifiers and power supplies, while high frequency transistors conduct small signals which operate at high frequencies, and they're going to be used at high speed switching applications and only high speed. Both of these are also going to be available in NPN and PNP. At the top of the line, we can talk about phototransistors. So phototransistors are going to be quite different from the functions we've talked about just now. Phototransistors are going to operate depending on the light, meaning that they're going to be light sensitive, versus the rest, which have been at the base of the terminal. Then phototransistors are available in both BJT and FET transistor types. And lastly, we have unijunction transistors, known as UJTs. They're going to be electrically controlled switches, and these transistors do not contain any amplification characteristics. So both of these are very different from the more simpler functionalities of transistors, and there's just so many functions with transistors that it allows us to use them for so many different applications. Now we can move on to Adam, and Adam is going to tell us about how we can use transistors.
Use of transistors. Transistor is one of the most important devices ever to be invented. Now, here is an analogy to understand their use. When watering your garden, you control the water pressure with the faucet valve. Well, transistors act the same way. They allow us to control how much current goes in a circuit, all of it, some of it, or not at all. We do so by controlling the voltage across the transistor lead. Let's go over a quick example. Here we have a basic circuit with a battery and a light bulb. The current flows normally without interruption. We can add a switch to control when the current should flow or not. But the problem is that it requires a human. What if we use a transistor instead? Well, notice that the transistor is not allowing the current to flow. So how do we make it work? When we apply a small voltage to the base lead of the transistor, the current in the main circuit flows properly. Notice here we have two circuits, the main circuit and then the circuit of the transistor with the small voltage. Here is a more practical example on a breadboard. Typically a voltage between 0.6 and 0.7 applied to the base lead will turn on the transistor. In this example, we're only applying 0.5 volt, which is not enough to make the transistor allow the current to flow in the main circuit. When we apply 0.6 volt, the current is now flowing, but the light bulb is dim. The reason why is because the current is not flowing at full capacity. So we need to increase the voltage we're applying on the transistor. We can see here that when 0.7 volt are applied, the light bulb is now bright. The transistor also acts as an amplifier. When used in an electric circuit, we use a small voltage to control a large voltage. So we can also use this property with signals. So we input a small signal and we get a larger output signal. That's what speakers are used for.
Hi everyone, my name is Todd with the Transistor Group here, and I'm ready to show you guys the math, the fun bit, the part you've been waiting for in this presentation. How do we do math with the transistors, Todd? Well, I'm ready to show you with my MS Paint drawing. First, I must clarify a few things. This is a kind of typical example of an NPN transistor. You heard about the many different kinds of transistors. I'm here to focus on just this one, a common one for a lot of basic physics problems. I mean, you'll see, of course, many different ones throughout your book or real life examples, but this is kind of what our class might cover if it were to cover transistors. So this is what we're going to be doing here. Maybe you're familiar with the letterings. You kind of see some of this stuff going on. This C is the collectors that you've hopefully heard about, and the emitter as well. This is the base, the transistor, whatever you want to call it. Beta is what it's represented by. I know it looks like a B. I promise you it's beta. Ignore that for now. Let's kind of just keep moving here and keep rolling. You can see that one thing about the NPN transistors here, as opposed to other transistors, is that the direction of the emitter current is actually denoted by the emitter arrow. So normally, not normally, sorry, in other examples, the emitter arrow will face inward towards the base, towards the center, and the current will not denote that. But with NPN transistors, direction of the blue arrow is direction of the current, and you can figure everything else out from there. If we treat this centerpiece as a junction, we can use some Kirchhoff's laws, some Kirchhoff's rules. When we know that the collector current flows down towards the center, the base current flows in to the center. That means they have to combine together here, and this is the second equation, to create the emitter current is equal to the base current plus the collector current. What is different and what is unique that you guys need to know about transistors is that the collector current for NPN transistors will be equal to beta, some constant, it is unitless, times the current from the emitter, sorry, not the emitter, the voltage coming into the base, or the current coming into the base from the voltage times the resistor that is set up in your circuit. Sometimes these will be closed, sometimes the collector will be grounded, but that is not what is going on in this example, just for heads up. Sometimes you will also see that beta is represented by the letters HFE. Again, this is not a unit, this is just how it is written out. Most people prefer HFE. Beta is one letter. I chose to write it as beta because it's a lot easier for me and a lot easier to say than HFE, especially when it's unitless. Anyway, going into the Kirchhoff's rules here, I commented on these two. We can substitute out the collector current in the second equation after the junction and find out that the emitter current is actually equal to the base current, the transistor current, times beta plus 1. And we realize that ideally as well, in that the transistor is an increasing current. So we have two currents flowing together, and they combine to create the emitter current. And one way we can do that, oops, sorry, I clicked on the wrong slide there. I went too far ahead, is with an example. Let's take a beta or an HFE of 200. Again, it's unitless. And a beta current, or current sub beta, of 50 milliamps. We plug them into the two equations that I mentioned before, or the three equations, sorry, and we can get a collector current of 10 milliamps versus an emitter current of 10.05 milliamps. Again, the math for it doesn't really matter too much. What's important ideally is that the collector current in an NPN transistor is roughly equal to the emitter current. And we can see that in that, we can see in that we get a 200 times 50 here and a 200 times 50 here, but a 50 plus 1. So it's really a minor difference, especially if the current is so small, such as 50 milliamps, which is, microamps, which is most of our cases here. You'll see commonly that people say collector current is roughly equal to the emitter current. And that's really all you need to know about transistors, and that's likely the reason why we're not covering it in our class, is that the math for it doesn't seem to matter too much. Sorry, hopefully I didn't scare you too much with my MS Paint drawings, and hopefully everything else went well in the presentation. Thank you all for your time. Have a wonderful day.